Hi, our presentation is about the real-life situation of the 2018 Quasar Bell test experiment.
Before we get into our real-life situation, we wanted to make sure that everyone is clear on the basics of quantum entanglement. Quantum entanglement is a branch of quantum mechanics and is based on entangled particles and the relationships between them. Quantum mechanics is a branch of mechanics that deals with the mathematical description of the motion and interaction of subatomic particles, incorporating the concepts of quantization energy, wave-particle duality, the uncertainty principle, and the correspondence principle. When two or more particles, such as electrons or photons, interact physically, they become entangled. These particles then act in accordance with one another. Suppose that there are two entangled particles. Both exist in, let's say, red and blue simultaneously. This means that each particle is both the color red and the color blue, while they are not being detected by a color detector. The instant that one particle is detected, it takes on one color, either red or blue. When one particle is detected and turns red, the other particle instantaneously turns blue. This can be possible even when both particles are light years away from one another, breaking both time and distance barriers.
When two particles are entangled, they are simultaneously and inversely correlated with one another. Whatever happens to one particle will immediately influence the other. As shown on the picture on the slide, particles can have a spin in a certain direction depending on how it's being influenced. For example, they can spin at a 0-degree angle, a 45-degree angle, a 90-degree angle, or even a 135-degree angle. Depending on how one particle spins, the other will spin at a proportional angle to 90 degrees. This means that if you have two particles, particle number 1 and particle number 2, if particle number 1 spins up, then particle number 2 will spin right. And if particle number 1 spins down, then particle number 2 will spin left. This is the relationship that we call entanglement. Particles are naturally entangled in our universe in atoms. Every atom, by law, contains electrons that are entangled with one another. Scientists can also artificially entangle particles, as done by many scientists already.
This all began when some of the greatest scientific minds of the past started delving into the mechanics of quantum physics, as well as the implications that came along with it. Erwin Schrödinger first discovered the basics of quantum entanglement through a commonly known thought experiment called Schrödinger's cat. The rudiments of this experiment revolved around the fact that if you put a cat and poison inside of a box, hidden from your sight, you won't know whether the cat is alive or dead until you open the box. Schrödinger proposed that the cat is both dead and alive at the same time until it's checked on. The moment that someone checks on the cat, it either takes the form of being alive or being dead, depending on whether the cat drank the poison or not. In this situation, the entangled particles are signified by the cat and the bottle of poison. If the cat is alive, the bottle of poison should still be full when the box is opened, and if the cat is dead, the bottle of poison should be empty. The outcome of one depends completely on the outcome of the other. His concept was further added on to by Albert Einstein. In fact, this concept spooked Einstein out so much that he labeled it as spooky action at a distance. The phrase spooky action at a distance is used to describe the ability of separated objects to share a condition or state, thus quantum entanglement. Einstein, for one, didn't believe that such a phenomenon was possible, and disagreed with arguments that Schrödinger made. Niels Bohr, another well-renowned scientist during the time, agreed with Einstein and believed that quantum entanglement was indeed possible. In his perspective, atoms could be entangled no matter the distance between them. Whatever you do to one particle, there will be an inverse effect on the other. One of the biggest issues that Einstein had with the theory of quantum entanglement was how it surpassed the speed of light barrier. Even when the particles are light years apart, information from one particle to another travels instantaneously, and therefore faster than the speed of light, which Einstein believed to be the fastest traveling particle in our universe.
The Bell experiment was created by John Stuart Bell in an effort to verify quantum entanglement through a constructive method. Many various Bell tests were conducted over time, each attempt reducing external variables that may have affected the results. The 2018 Quasar Bell test, conducted by David Kaiser and his team on the Canary Islands of Spain, proved to close all known loopholes, more importantly, the freedom of choice loophole. When conducting the Quasar Bell experiment, the team felt that it was vital to reduce chances of error, such as unknown variables and inherent bias. In order to achieve this and eliminate any possible loophole, they made it a priority to make the experiment as random as possible, thus reducing any chance of bias.
The experiment revolved around a source emitting two entangled photons through a photon color detector with varying settings based on the light from distant quasars coming in through the telescopes. The color detectors were named Alice and Bob, whose settings changed in accordance with the light from the quasars. Quasars are a massive and extremely remote celestial object, emitting exceptionally large amounts of energy and typically having a star-like image in a telescope. It has been suggested that quasars contain massive energy black holes and may represent a stage in the evolution of some galaxies. The telescopes were distanced a mile away from each other in order to ensure that the spooky action does indeed act at a distance. Using quasars to randomize the settings on the color detectors effectively eliminates the freedom of choice loophole, which was present in previous Bell experiments. This is because the quasars are light years away, making the light coming in through the telescope 300 years old, which makes it pure and uninfluenced by humans.
This real-life situation has led us to our knowledge question. Does production of new knowledge lead to more uncertainties or make things more certain? Interestingly enough, there are many ways you could tackle this question, but we chose to focus on the two areas of knowledge that we felt were most prominent: natural sciences as well as history. In order to answer our knowledge question to the fullest extent, it is important to first unpack our knowledge question and thoroughly examine it. Firstly, we must understand the key terms of our knowledge question. The term uncertainties refers to the doubt that one may feel towards a certain piece of knowledge. The term certain, on the other hand, refers to the scale of doubt. The less doubt an individual has, the more certain they can be. Understanding new knowledge is also important when answering the knowledge question. New knowledge is knowledge that is produced through rigorous testing, peer review, and careful examination of the study, and is knowledge that has not already present during the time of an event.
The first area of knowledge that we are going to cover is the natural sciences. The natural sciences are areas of study based on the world around us and the observable human aspects of it. The first concept that we will cover in the natural sciences is the scientific method. The scientific method is the methodology that scientists have created in order to ensure rigorous testing to come to a solid conclusion based on multiple tests and peer review. The scientific method starts out with a problem that needs explanation, through which a hypothesis is created, and then tested rigorously. If the hypothesis survives, then laws and theories can be formed from it, which all contribute to a common paradigm. If the hypothesis does not survive, anomalies are created, which could contribute to the creation of an alternate theory, leading to a paradigm shift. In the case of the natural sciences, the scientific method can be representative of the actions scientists must take when conducting the Quasar Bell experiment. The first few ways of knowing that we wanted to focus on pertaining to the natural sciences are intuition, reason, and sense perception. Intuition is oftentimes also classified as immediate cognition. This is knowledge which is immediately evident without interference or evidence. Intuition is regularly used in the natural sciences to back up any claims that scientists may have made. Another way of knowing that is very important to the natural sciences and our real-life situation is reason. Reason is best defined as how we understand it to be, the way of knowing which involves us trying to make sense of the world using logic, rationality, comparison, judgment, and experience. Reason is commonly used to make sense of the results of tests and experiments. Natural sciences usually use deductive reasoning to test and find axioms. They then use inductive reasoning to test based on previously made axioms using the deductive reasoning. The problem with this method is that the data could be misunderstood or misinterpreted if there is not much knowledge in a particular field of study, causing the developed axioms to be wrong and in turn throwing off the field of study. Finally, the last way of knowing that we felt tied this all together the best was sense perception. Sense perception can be defined as understanding gained through the use of the senses such as sight, taste, touch, or hearing. Sense perception is essential to the observation process of the scientific method. It allows scientists to observe data first-handedly and make deductions from that data. However, human sense perception can be faulty and cause people to make faulty judgments when their sense perceptions fail them.
The second area of knowledge that we felt was important to our real-life situation is history. History is best defined as the study of the recorded past. It raises knowledge questions such as whether it is possible to talk meaningfully about a historical fact and what such a fact might be, or how far we can speak with certainty about anything in the past. This area of knowledge has an enormous impact on a real-life situation as new evidence and hypotheses come out over time. An overall view of scientists as well as what is considered right and wrong also changes. This can be defined as revised interpretation, or the study of the methods of historians in developing history as an academic discipline, and by extension is any body of historical work on a particular subject. As new evidence is collected, the way that an event happened becomes more supported or less supported. There is enough evidence to overthrow the common interpretation of evidence. Then the event that happened must be revised. This is similar to a paradigm shift in the notion that new, more accurate theories and evidence can change the whole situation. Most problems that can be related to history as a way of knowing are biases. Some of the most common biases that can affect the historical development of an event. Topic choice bias and confirmation bias are two important biases that a historian could have when interpreting a historical event. Topic choice bias occurs when the topic chosen by the historian is too narrow or more favorable to one side of the story. This could make the whole interpretation skewed to one perspective, not showing the multiple perspectives needed to make the historical situation more accurate. Moreover, if a historian is looking for a situation to be a certain way, they may be more prone to finding evidence to support their interpretation, causing confirmation bias. Historians may also add in their own inherent bias in terms of how they interpret history. This can be either voluntary or involuntary, but can still occur subconsciously. There are various ways of knowing that are commonly used in the human sciences that are relevant to how scientists must think when conducting such experiments. First of all, the way of knowing emotion is very important because the way that a historian feels about a certain event may cause them to find evidence to support their emotions, as I mentioned in the previous slide. Moreover, emotion can cause a historian to be passionate about the area of study, causing either them to find the best fitting interpretation possible for an event, or causing them to find evidence to support how they would like it to be. The second possibility is shown as falsification. Secondly, the way of knowing of imagination is also very essential to historians because they must be able to think of all the possible ways in which a situation could have occurred. This can also be dangerous, however. If a historian gets too attached to their imagined interpretation, they may have a confirmation bias when finding evidence to support their interpretation. Language has an enormous impact on history as well. The way something is phrased can either reveal or hide information and carry biases such as national bias that is also commonly seen in history textbooks.
In conclusion, new knowledge can sometimes lead to more certainties, such as knowledge produced from rigorous scientific testing based on a specific previously constructed paradigm. This new knowledge would make previous knowledge more certain as it supports the current paradigm. However, in some instances, such as with our real-life situation, new knowledge can contradict the current paradigm, causing a scientific crisis and eventually a paradigm shift. This new knowledge can therefore make previously produced knowledge uncertain, but make any knowledge that may be produced in the future pertaining to the field of study more certain.